In this section, we'll first look at homogeneous systems, and then we'll look at non-homogeneous systems. So a homogeneous system, all that means is that your right-hand side is zeros. So this first exercise says describe all solutions of AX equals 0. So this is homogeneous. And we're going to write the solution in parametric vector form. And it gives us that A, like our A here, is row equivalent to this matrix. So keep in mind this A is a coefficient matrix. So you're told that this is row equivalent to the original. If I augment it with zeros, row reduction will not change that. So some people like to put those zeros there just to remind yourself that they are there. I'm going to row reduce this one more step. I want to change that -3 to a 0. So I'm going to take row 1 equals row 1 plus 3 row 2. From here, I can see that my x3 has no leading one or no pivot, and my x4 also doesn't. So both of those are free variables. So I'm going to say x3 is free and x4 is free. So rewriting the first equation, I have that x1 minus 2x3 minus 7x4 is 0. So I can solve that for x1, and I get 2x3 plus 7x4. And the second row tells me that x2 plus 2x3 minus 4x4 is 0. Solving that one for x2, I get -2x3 plus 4x4. So when we think about writing a solution, we know that our solution has 4 variables, so x1, x2, x3, x4. My x1 can be written as 2x3 plus 7x4. My x2 can be written as -2x3 plus 4x4. My x3 is free, and my x4 is x4. So to write this in parametric form, I'm going to split it up into the free variables. So x3 times some vector plus x4 times some vector. So I'm going to look at the coefficients of x3, and I get 2, -2, 1, 0. And the coefficients of x4 are 7, 4, 0, 1. So this is in parametric form. In exercise 2, they give you 2 homogeneous systems. Again, homogeneous because the right-hand sides are 0. And the question is, without doing any row reduction, do you know a vector that will solve each system? So if x1, x2, and x3 equals 0, so 0, 0, 0, will always solve a homogeneous system. The question is that the only solution, or is it just one of many? 0, 0, 0 is called the trivial solution. Trivial meaning it's so easy we don't usually talk about it. So of course 0, 0, 0 is going to solve them. Let's worry about the more interesting ones. So in this next part, we're given row reduced forms of these systems that we just had, and we want to know, does either one of them have a non-trivial solution? In other words, I know that 0, 0, 0 is a solution to both of these. Are there any others? So looking at this reduced form on the first one, I can see that I have a free variable. So I see that x3 is free, which means I will have infinitely many solutions. So there are non-trivial solutions. In the second one, I see that I have 3 pivots. This 0, 0, 0 is right-hand side. That tells me, x3 is 0, x2 is 0, x1 is 0. There is no free variable, so this has only the trivial solution. In exercise 3, we have one equation. It is equal to 0, so it is homogeneous. And I want to just write this as in parametric form. So we could think of it as this matrix, and there's a free variable for x2 and a free variable for x3. And then if I rewrite that first equation, I'm going to get the same thing I just had, but I'm going to just rewrite it a little bit. So I'm going to say x1 is equal to negative 3x2, plus 3x2 minus 5x3, because I'm putting them on the other side of the equation. So when I have x1, x2, x3, writing this in parametric form, I first have 3x2 minus 5x3. x2 and x3 are free. Now writing in parametric form, the coefficients of x2 are 3, 1, 0. And the coefficients of x3 are negative 5, 0, 1. So what this tells me is that this is a plane in R3, and it contains the origin, partly because it's homogeneous, so we know that 0, 0, 0 does satisfy it. And then it's parallel to 3, 1, 0, negative 5, 0, 1. So again, I think about this as being a plane because if it's parallel to these two vectors, the two vectors are going to create a plane, and then I'm parallel to that, again, going through the origin. This next problem is essentially the same thing. Notice that this equation is the same, except that I changed the 0 to 4. So this is a non-homogeneous system. I say system, but it's a very simple system. And what we're going to do is the same thing. I'm going to write the solution in parametric form. So we saw before, solving for x1, we can, instead of having 0, I'm going to have 4 plus 3 x2 plus minus 5x3. So writing the solution, I know I have x1, x2, and x3. x1 is 4 plus 3x2 minus 5x3. x2 is free, x3 is free. Writing this in parametric form, I'm going to get 4, 0, 0 plus x2 times 3, 1, 0 plus x3 times negative 5, 1, 0, 1. So notice that this is very similar to the solution. Just to point out that this piece is the same as what we have right here. So the thing that's different is this 4, 0, 0 out front. So this will be a plane in R3 containing the point 4, 0, 0, and then it's parallel to the vectors 3, 1, 0, negative 5, 0, 1. So really what's happened here is just whether or not you're going through the origin or through another point. So a homogeneous system and a non-homogeneous system are very similar. We just have this extra shift, which we'll visualize that in another problem. So theorem 6 is trying to capture what this is happening. It says, suppose ax equals b is consistent. Remember, consistent means has a solution. So it has some solution for a given b, and let p be some student. They use p for particular solution. Then the solution set of ax equals b is the set of all vectors of this form. So the particular solution plus the solution to the homogeneous system, which again, in our example, the 4, 0, 0 was our particular solution, and then that x2 and x3 piece was the homogeneous solution. So again, we'll look at this next example on Desmos, but we can think of that particular solution as translating the homogeneous solution in the plane. So, if your solution is a line, so this black line is supposed to represent the solution to ax equals 0, and then to solve ax equals b, it's just a line parallel to that. Or if you have a plane, that plane is the solution to x equals 0, well then the solution to x equals b would be some shift of that same plane. All right, so let's go ahead and solve this system. 1, 3, 1, 1, negative 4, negative 9, 2, negative 1, 0, negative 3, negative 6, negative 3. If we row reduce this, we will get 1, 0, negative 5, negative 2, 0, 1, 2, 1, 0, 0, 0, 0. So I see there's a free variable, so it tells me there's going to be this infinitely many solutions, so x3 is free. Writing out that first equation, I have x1 equals negative 2 plus 5x3, and x2 is equal to 1 minus 2x3. So writing this in vector form or parametric form, so x1 is the negative 2 plus 5x3, x2 is 1 minus 2x3, and then x3 is free. Rewriting that as some vector plus x3 times some vector. So my constants are negative 2, 1, 0, and the coefficients of x3 are 5, negative 2, 1. So what this is saying is that, so because this is a line, think about the span of one vector, the solution is a line in R3 through the point and parallel to 5, negative 2, 1. So let's take a look at this. All right, so I am using Desmos 3D, which is relatively new. You can just Google Desmos 3D and you can play around with it. So I typed in the first equation. So there's the plane in R2. I plot the other one. So those two planes, you can see they intersect at a line. If I graph the other one, you can see that all three of them intersect at a line. We saw that the solution was a line in R3 that's through the point negative 2, 1, 0 and parallel to 5, negative 2, 1. So I wanted to plot the vector 5, negative 2, 1 and see that the line is parallel to it. So you can kind of see that the line where they all intersect is parallel to that purple line that is the vector 5, negative 2, 1.